All right, the first part of 7. This video is just going to cover the first part of 7.3, kind of laying the foundation for the sampling distribution of sample means. That would be the collection of sample means. Take samples of size 10, collect one sample, that gives you one value, 1 point estimate. Collect a whole bunch, that gives you a picture of the sampling distribution. Collect every possible combination of sample size, whatever, and that gives you the entire sampling distribution. We're going to study those. The display on the left shows the distribution of incomes in a population of 61,000 households. As you can see, most households are earning anywhere from 0 to 100,000. But we got some people that make a lot of money. Nobody makes less than 0. So we get a skewed right distribution. Suppose we collect a simple random sample of size 100 from this population. So we're going to select 100 households from that population. We're going to find the X bar, and we're going to record the X bar on this graph. So this is the sampling distribution of the sample means. It's a collection of X bars. Instead of a dot plot, though, they're making a histogram. So as you can see, this has got quite a bit of variability, and it looks like it's skewed to the right. This has much less variability, and it doesn't really look to me like it's skewed at all. We're just talking about it, though, here to start. Notice, the variability of the sampling distribution is much less than the population distribution. So this, I guess, I think I said someplace here. However, they're centered at the same spot. They're both centered at the true population mean, right? They're both centered at the true. If the center of the sampling, if the mean of the sampling distribution is the population mean, then that tells you that X bar is an unbiased estimator of mu. This graph displays an important fact about statistics. Averages are less variable than population values. Okay, that's common sense. So what does the sampling distribution of sample means look like? Well, the center and spread are fairly easy. However, the shape is a bit more complicated. Okay. Suppose that X bar is the mean of a simple random sample drawn from a large population with mean mu and standard deviation sigma. Then the mean of the sampling distribution of X bar is the mean of my sample means is the true population mean. This tells you that X bar, I think I'll say this later, I'll just say it. It tells you that X bar is an unbiased estimator of mu. But the condition is you have to have a simple random sample, right? You have to have a good sample. If you take a biased sample, then your sample means may be bigger or smaller than the population mean more regularly. The second one is the standard deviation. The standard deviation of your X bars, and this is a new formula for us. I'm at 3 minutes. I do want to kind of talk about, this is an important formula. I do want to talk about where it comes from. This is kind of a not needed type of thing, but you should kind of know where it comes from. So suppose I take a sample of size, I don't know, 10. To calculate X bar, I'm going to take my X1 plus my X2 plus my X3 plus my da-da-da-da-da all the way up to X of 10. Then I'm going to divide by N. So let's call the sum just the X1 plus the X2 plus the X3, right? So this is just a random variable. It's a combination of 10 other random variables. So if I wanted to find the variance of the sum, I would simply add together the variances, suppose X, whatever the random variable is, but suppose the mean of X is mu, and suppose the standard deviation of X is sigma. Well, if I want to find the variance of the sum of these 10 things added together, if these are independent variables, then I can simply add their variances. So that'd be sigma squared plus sigma squared plus, they're all the same random variable, so they're all going to be sigma squared, right? And there's going to be 10 of them, so this is simply going to be 10 times the standard, the variance squared. Then if I want the standard deviation of the sum, I would simply square root it, which is going to give me the square root of 10 times sigma squared, okay? But I want the standard deviation of the mean. Well, the mean isn't just the sum, it's the sum divided by n. So if I wanted the standard deviation of my x bars, then I would take this standard deviation. Oops, sorry, I should have got rid of that square there, right? Square root of a sigma squared. But then I'd want to, then I'm multiplying by a constant. So the spreads are multiplied by the same constant or divided by the same constant. So then I need to divide by the square, divide by 10. And the square root of 10 over 10, that's if we put this under a square root, basically that gives you sig over the square root of 10, which is basically the standard deviation of your original variable divided by the square root of your sample size. Again, this isn't really needed, but it comes from adding random variables together, adding 10 of the same random variables together. We did that. So this is the formula, but this is the formula only if we have independence, because if we don't have independence, then I can't add these variances together. So to go back, you don't need to know all that crap, but what you do need to know is this is a formula, and you need to have independence in order to use it. What is independence? Well, if you take a sample of size 10 from a population of size 15, you don't have independence. Because once you take 10 people, every time you take a person out of that population and you're sampling without replacement, you're kind of changing the mean and spread of the population that you're sampling from. So that would be no independence. Technically, you don't have independence ever. But if your population is really big, let's say 2,000, now it doesn't really matter if you take out one person or two people or even 10 people because the population is so big. So although we don't have independence, we kind of have this pseudo-independence. So this formula can be used as long as we satisfy the 10% condition. Okay? So what do you need to know? Hopefully you understand kind of why all these things were. But what you need to know is this is the formula for the spread, and it's dependent upon independence, aka it's dependent upon the 10% condition being satisfied. That my sample size is less than 10% of the population size. Then I have pseudo-independence. Okay? So this is the center, and this is the spread. Now we just need to talk about shape. Shape's a little bit complex. Might wait till the next video. Let's just do this example and talk about this summary here. So this is going to kind of summarize the things that I just talked about. Summary. The sample mean is an unbiased estimator of the population mean if we have a simple random sample. Or oftentimes, guys, it's just okay if we have a random sample. Technically, we need a simple random sample. But basically, as long as we have a good sample, and as long as we're using a random sample, like as long as every individual's got the same chance of being selected, then we're probably okay. We're not just picking people that we know. So, unbiased estimator, what does that mean? That means the average of my sample averages, the mean of my sample averages, is going to be centered at the true population mean, unbiased, just like it was with proportions. As n increases, the spread of the sampling distribution x bar decreases. Why? Well, we got a square root of n factor on the bottom of, oops, sorry, crossed it out there, tried to highlight it. I got a square root of n on the bottom of my formula. So as n increases, it's going to decrease the standard deviation of the sampling distribution. But we already know that. If you sample more people, you get a better estimate. You get an estimate that is probably going to be closer to the true mean. It's going to be less spread out. This means that if you take larger samples, your sample mean is likely to be closer to the true mean. However, you need to quadruple the sample size to half the standard deviation. It's because of that square root factor right there on the bottom. If you want to half your standard deviation, you got to increase your sample size by a factor of 4 because the square root of 4 is 2. You should use this formula only when the 10% condition is satisfied, as this formula requires independence or pseudo-independence. The spread, the center and spread of the sampling distribution of x bar is as stated above, no matter what the shape of the sampling distribution is. The next thing we're going to talk about is shape, but it is important that you understand that these things are always true. This as long as this as long as this, regardless of the shape. So if the shape doesn't work out, these top two things are going to be true as long as those are true. All right, going to the movies. Just a quick example here, and then we'll leave the shape for class or the next video. Going to the movies. Suppose that the number of movies viewed in the last year by high school students has an average of, so let's say X is the number of movies viewed. Probably don't need to do this, but I kind of like it. And the mean of my X's is 19.3. And the standard deviation of my X's is 15.8 movies. Suppose we take a simple random sample of size 100. Calculate the mean number of movies viewed by the members of the sample. Label the measures. Well, I guess I did need to do it. I'm trying to highlight and I'm just crossing stuff out. So that's what I did right here. I labeled these measures using proper notation. I think that's important. But they are parameters. They are true means and true standard deviations. What is the center of the sampling distribution? Check the necessary condition. Well, number one, the center. The mean of my X bars is equal to the mean of my population. That's this formula right here. I called it mu sub X, but it's the same thing. The mean of my sample means is equal to the true population mean. So that is 19.3 movies. No work really needs to be shown there. And check the necessary conditions. X bar is going to be an unbiased estimator of mu, as long as we took a simple random sample, took an SRS, right? We took a good sample, so our values, our means should be centered about the right spot, and it said we did. What is the standard deviation of the sampling distribution? Number two, what is the spread? This formula is on your formula sheet, of course, but we're just going to, you should be able to kind of remember it, but whatever. Sigma of X bar is sigma of X over the square root of N. In this problem, that would be 15.8 divided by the square root of 100. That is 15.8 divided by 10, which is 1.58 movies. Check the necessary conditions. This formula is only valid if you have independence. So let's check it. My sample size was 100. Well, what I don't know is I don't know how many kids were in this high school. If this is a small high school like ours, I think we're going to have problems. And it didn't really say that it was a large high school. So I don't know if this condition may fail. I'm going to say if n equals 100 is less than 10% of all high school students at this school, then we're okay. Then the conditions are met. However, if we have less than 100, I guess the magic number here is 1,000 kids, right? As long as we have 1,000 kids. If we have less than 1,000 kids, though, then this formula can't be used and this number isn't quite right. Now we're going to learn kind of what happens whenever the 10% condition fails, and it's actually not so bad. In fact, this, it's almost going to be, basically whenever the 10% condition fails, this spread is actually going to be larger than the spread that we get is going to be larger than the spread that the spread given by the formula will actually be more than the actual spread of our sampling distribution, meaning our estimates are actually going to be better than we would expect. But let's just not worry about that here right now. So when I select an individual, the number of movies that they watch could deviate on average about 16 movies from the mean. However, when I take an average of 100 kids, those sample averages should only deviate on average by about 1.5 movies from the true population mean. So that means usually, on average, I'm about 1.5 movies away from the true mean. Now, I could be 2 or 3 movies away, or I could be half a movie away, or I could be right on. But on average, I'm going to be about 1.5 away. Okay?